let's start with problem 4. So in this problem, we're gonna dealing with some graph. So I'm gonna introduce you to some basic concept about the graph, and this is kind of like a spoiler alert because later on I also have to create another video that's gonna teach you everything about the graph. So basically, the graph needs to have a node and the edge. The node and the edge. So now the question asks you, how many set of nodes can be created from the end node graph? So for this graph right here, there are 5 nodes, which is 1, 2, 3, 4, 5. So this is going to be 5 node graph. And also, what is the set? Set is actually the collection of items. So set of node is a collection of node. And what's special about this set of node is that it has to be formed from the end node graph. So the set need to contain the node inside the graph in the image. Everything beside this graph is gonna be invalid. For example, we have the set of 1, 2, and 3. So you can see it had node 1, node 2, and node 3, which is inside the graph. So 1, 2, 3. So this is a valid set. Now let's have another example. Let's say 5 and 4. So 5 and 4 are inside this graph. So it's valid. Now let's have 1, 2, and 5. So you can see 1 right here, 2 right here, 5 right here. So they are valid. Now let's say you have 9, 1, 2. What's gonna happen? So 1 and 2 are inside the graph. You can see it right here, node 1 and node 2. But 9, we didn't see it at all. So that's why this is not a valid set. So basically, this is how you can form the setup node from the given graph. Now let's come back to the problem. It asks how many setup nodes you can generate from the graph. So which means you can have more, let's say 1, 2, 3, 4, and 1, 5, 4, and many more. So in order to solve this problem, I'm gonna use some trick in order to express the set in a new way. So you can see, since this is a 5 node graph, the largest set you can form is a set that have all the 5 nodes. So what should I write right here? Should have node 1, node 2, node 3, node 4, and node 5. This is the largest set that can be formed, which have all the nodes inside the graph. So now let's have some rule in order to solve this problem. I'm gonna set 1 is when the node inside the set, and 0 is when the node is not inside the set. Okay, for example, let's say I put number 1 right here and number 1 right here, everything else 0. This means that node number 1 gonna be inside the set, node number 3 gonna be inside the set, but node number 2 and 4 and 5 are not inside the set. Therefore, the set gonna look like this, which is 1 and 3. You have node 1 and node 3. Since number 1 is in here, and we already agreed that like number 1 is when the node is inside the set, and 0 is when the node not inside the set. Let's have some other example. Let's say you have 1 right here, 0, 0, 0. So 0 in node 1, so node 1 should not be included in the set. But node 2 had number 1, so it should be included, and node 4 is included, so it should be. Therefore, your set is going to be 2 and 4. Everything is 0, so you don't include inside. And for 0, 0, 1, 0, 0, this only have node 3. And if node 3 is 0, then it's just an empty set, which has nothing. And you can also guess when of the position filled with number 1, then the set gonna contain 1, 2, 3, 4, and 5, which is all the nodes inside the 5 node graph given. This is when the case gonna be 1, 1, 1, 1, 1. So now let's add this question from 0, 0, 0, 0, 0 until 1, 1, 1, 1, 1. How many numbers that you can generate between those two? And if you look at this, just remind you of the binary number. So in order to find all the possible binary number that have 5 bits in this case, you can see N1, N2, N3, N4, N5. It's like represent a 5 bit of binary number. You're just using 2 power 5. So you can see from this basic setup node problem, you can convert it to binary generation problems. So for the graph with n node, the formula is gonna be 2 power n. And therefore, this is just like solving how many ways to generate a binary number of n bit. So you can see from a complex problem of like setup node, we can break it down to just a simple binary generation problems. And since it takes 2 power n to generate all the setup node from the n node graph, therefore the runtime is 2 power n. So for problem 5, which is the extension of problem 4. So in problem 4, you kind of like have some basic understanding of setup node that can be generated from the n node graph. In problem 5, we're going to ask you to check if your setup node is an independent set. So what is an independent set? Independent set is a setup node in a graph that any pair of nodes do not share an edge. So what do I mean by that? Let's have some example for you to see what's going on. Let's say I have a setup 1, 2, and 3. Before that, you have to make sure it's a setup node that can be generated from the n node graph. So this graph right here is actually the 5 node graph, and 1, 2, and 3 also inside this graph. Therefore, this is a valid setup node. Now let's check if it is independent set. So we have to make sure that like any pair of nodes will not share any common edge. So let's start with pair 1 and 2. 1 and 2. So you can see they have the edge, but this edge connect to node 5. They are not like connected together like this. Therefore, 1 and 2 are not sharing any common edge. So one set of pair pass. Now let's try 2 and 3. So 2, I have 3 right here. Again, those nodes got separated by node 5 in the middle, and it's only valid if there are some line like this. But in this graph, there's no such thing. So 2 and 3 are not sharing any common edge. Now let's try 1 and 3. Again, they separated by node 5 in the middle, and it's only work if there are some line in the middle like this. But in this graph, there's no such thing. So after checking all the possible pair of nodes, I didn't see any common edge between them. Therefore, this is an independent set. So now, before solving this problem, let's create the largest set that you can generate from this graph, which is 1, 2, 3, 4, 5. And this is valid because it contains all the nodes from this graph. And why we using the largest set? Because in engineering or in computer science, we care about the worst case scenario. So the worst case scenario is always when the data is like the largest. So in this case, our data is gonna be the set, and we want to make it as largest as possible. So in this case, the largest is gonna be 5 elements, or in general, it's gonna be n element for n node graph. Okay. So as you recall on how I finding the independent set, I have to like checking if any possible pair having any common edge. If there are some common edge on like any of the pair, then it's not an independent set. So basically, the algorithm for this is gonna like checking all the possible pair, like 2 and 4, 2 and 5, 1 and 3, 4 and 2, and etc. And checking all the possible pair kind of like reminded you of problem 2, just asking to find the pair of cities that giving the shortest distance. Because you can model this problem as a map of the second problem. So each node right here is gonna be the city. Instead of asking those two cities right here, oh, are you the shortest? Oh, are you the shortest? Oh, are you the shortest? In this problem 5, gonna ask, oh, are you share a common edge? Are you share a common edge? or you share the common edge, or you share the common edge. So you can see those two problems kind of like similar to each other. One just asking like if any pair are the shortest distance, and this one gonna ask if any pair share any common edge. Therefore, this problem is similar to problem 2, in which we find all the possible pair in n city, and then later on we're gonna determine which pair gonna be the shortest distance. And for this problem, we're trying to find all the possible pair from n node in the set. Later on, if any pair share a common edge, then it's not an independent set. Therefore, the runtime for this problem is also O(n squared, similar to problem 2. So now let's move to problem 6, which is harder than problem 4 and 5. In this problem, you have to find the largest independent set from the n node graph using brute force. And in real life, there are some algorithms that help you to find the largest independent set in the graph very quickly, but this time we're using a brute force approach in order to help you practice more runtime calculation, runtime analysis. So what is the largest independent set? So from problem 5, you already have like some basic understanding of independent set, which is the set that like any pair of the node in the set do not share any common edge between. So let's say the set of 1 and 2, there are no common edge between them due to the 5 node in the center. And after you find all the possible independent set, you want to pick the one with the greatest number of nodes. So in this graph, you can generate a lot of independent set. Let's say 1, 2, 1, 2, and 3, 4 and 3. And out of those 3, this one right here seems to be the largest because it have like 3 nodes compared to 1 and 2 and 4 and 3, which have like 2 nodes total, 2 here, and this one have 3. So for this graph right here, the largest independent set that you can find is the one that contains node 1, node 2, node 3, and node 4. So 1, 2, 3, 4. And you can see in this set, any possible pair doesn't have any common edge. If you look at the graph right here, and this set also contains like 4 nodes, which is very large compared to those 3 on the left. So this is going to be your largest independent set from this graph. So now let's solve this problem in a more formal way. So before finding the largest independent set, you have to know all the possible independent set. And after you find all the possible combination, you're gonna compare them against each other in order to find the set that has the most node. So before having all of the possible independent set, you have to generate all the possible set. So later on, you can filter out the independent one. And when you see all the possible set, remind you of problem 4, which we show how many possible set can be generated from the graph. And now, look at this picture. It's gonna be the graph that give it to you, and all the branch diverging from this graph, actually all the possible set. So 1, 2, 3 is actually the set from this graph because 1, 2, and 3 are inside the graph. Similar to 3 and 4, 1, 2, 3, and 4 because all these nodes are inside the graph. So this is kind of like the representation of all the set diverged or generated from the graph. So after you have all the set, you're gonna find all the possible independent set. So from 1, 2, and 3, let's check if they are independent set. So 1, 2, and 3 seem to be yes because none of these nodes have any direct common edge like this. So we're gonna circle right here to mark it as independent set. And now recall for problem 5, which is help us checking if a set is an independent set. Therefore, when we're checking the independent set right here, we kind of use the algorithms inside number 5. Similarly, for 3 and 4, it's also independent set, so that's why I circle. 1, 2, 3, 4, also independent set, and 2, 4, 1, also independent set. For 1, 5, and 4, they are not independent set because between 4 and 5, there are like a common edge between, and between 5 and 1, there's also a common edge between. Now let's check the runtime. So when the graph generate all the possible node, number 4, you recall the runtime gonna be 2 power n. Therefore, it takes 2 power n to generate all these possible sets. And when you check independent, if you recall from problem 5, the runtime gonna be n square. Therefore, it takes n square to checking if each of these sets are independent. N square right here, n square right here, right here, n square right here. But now, for the last step, you have to finding the largest independent set. So after checking if the set is independent or not, if it's yes, we're gonna compare the size of the set. So the size of the set gonna be 3 with the variable max that we create right here. The variable max gonna tracking which independent set is the largest. So the size of the guy right here is 3, you're gonna compare with max. And since 3 greater than max, you're gonna update into 3. And for the comparison operation, we already assume it's gonna be 1 second, so it's gonna be +1. Thus, the total time for checking independent and checking comparison, if it's independent, gonna be n squared plus 1. Now move to 3 and 4. Size 2. Since this is an independent set, therefore you have to do the comparison with the max. So 2 greater than max. Seems to be false, so that's why the max is stay the same. And this still +1 because you do the comparison due to the independent set. And now for 1, 2, 3, 4, the size is gonna be 4. And since it is an independent set, you're gonna do comparison with max again. 4 greater than max, so you're gonna update to 4. And it's gonna be +1 for the comparison. Now you move to here, 154. This time it's not an independent set, so you don't have to do the comparison. So you don't have to add 1. So it's gonna be just n square. Similar here, n square, and it's also an independent set, so you have to do +1 for the comparison. In the end, your max gonna be 4 because we show on the previous slide that 1, 2, 3, 4 actually the largest independent set. So now this is a more clean view of the problem that we resolved before. And if you notice, back then we had n squared plus 1, but in the long run, if n goes to infinity, it's n squared itself. So that's why I just simplified it to n squared for each node right here. And since there are 2 power n possible sets, and each set costs n squared to do the independent checking, therefore 2 power n times n squared gonna be your final answer. Therefore, the runtime to find the largest independent set gonna be n squared times 2 power n. So this is another way to explain the problem. This is more formal in algorithm style. First, I'm gonna find all the possible set of vertices formed by the graph. And from problem 4, we already showed that the total runtime gonna be 2 power n. And next, after finding all the possible sets, you're gonna check if each of them are independent. And we already show from problem 5, which has the runtime of n squared. And if it's yes, we just do comparison of the set size with the current max size. And for comparison operations, only constant 1 second, which we assumed on the previous video. All of these gonna give you this runtime. So this is general algorithms to solve the problem using brute force.